Well, this lecture introduces an overview of linear transformations. So linear mappings from one vector space to another plays a very important role in mathematics. You can imagine the linear mappings as functions in calculus 1 when a functions helps transform a set of values, right, to a different set of values under functions transformations or the function description. In a very similar fashion, a linear map transforms a set of vectors in one vector space to another vector space, or can be within the same vector space, right? You transform a set of vectors to a different set of vectors in a different space or in the same space under the mapping descriptions, this descriptions of the map. All right. So in the study of vector space, one of the very important types of mappings are linear transformations. Well, let's talk about the definitions of a linear map. So a map L from a vector space V into a vector space W is said to be a linear transformation if you apply the map L on the linear combinations of V1 and V2 with alpha and beta are the weights, then it's gonna be equals to alpha multiplied to the map L applied on V1 plus beta multiplied by the map L applied on V2. Again, for V1 and V2 are vectors in V, and scalar alpha and beta are constants in R. Again, in order to determine whether a map is a linear transformation, you need to make sure that if you apply the map L onto a linear combinations of V1 and V2 with alpha and beta are the weights, then this equals to alpha multiplied by L applies on V1 plus beta apply on V2. V1 and V2 are the two vectors in V, and alpha and beta are just constants or scalars. The notations that we usually use when talking about a linear map from a vector space to another vector space is if L is a mapping from V to W, then this is the notations that we can use for the map L. L goes from V to W. So it takes some vectors in the vector space V and is to some vectors in vector space W under a map descriptions. So if V and V are the same, right, we can prefer a linear transformations L from V to V as a linear operator on V. So you take a set of vectors in V and you map it to another set of vectors of V under a map description. It's called linear operator. Okay. For an example, if we let a map L be an operator defined by this descriptions, this description means if you take a vector in R2, any vectors in R2, and you apply a map L onto this vector, you produce a vector that is 2 times as big as the original vector, 2 times x, right? So if x is x1 and x2, then when you apply L onto this x, you will have 2 times x, which means you will have 2x1 and 2x2. Okay. So that's what this map does. Now, we want to show that this map here is a linear operator, which is a linear transformation from R2 to R2. Okay, and you want to provide geometric interpretations of this map. So I want to rewrite the notation so this map L from R2 to R2. Okay, and the descriptions of the map is Lx equals to 2 times x. In order to show that this map here is a linear operator, you need to show that this map satisfies these conditions. When you have two random vectors in R2 and two random scalars, alpha and beta, you need to make sure that this equations here is true. Okay, so again, we need to call out two vectors. Let v1 right equals to, let's say, x1, x2, and v2 is y1, y2. So these are the two vectors in R2, two random vectors in R2. They both in R2. And you have to call out alpha, beta are just scalar values in R. Okay. Now, in order to show that this equation is true, I need to start with one side and end up with another side at another side. So let's start with this side. So you have L alpha V1 plus beta V2. Okay. So what is alpha V1 plus beta E2? So alpha V1 is alpha x1, x2 plus beta y1, y2. And you want to apply the map L onto this vector. Okay. And then we have alpha x1 plus beta v1, y1. So after you apply the map L onto this vector, you get 2 times this vector. So what I get is L 2 times alpha x1 plus beta y1 and 2 times alpha x2 plus beta y2. So this is the result vector after you apply this map onto this linear combination. Okay, so this is the left side. I start with the left side, and the right side is somehow I need to show that the left side here equals to alpha L V1 plus beta L V2. By the definitions, I need to show that this equals to this. Okay. So let's keep going here. So I have 2, after I apply the map onto this linear combination vector, I get 2, this is my result. I need to show that this is equals to alpha plus LV1 plus beta times LV2. So from here, I can separate this vector into 2 different vectors. I can have 2 on the outside, right? And I have alpha x1, alpha x2 plus 2 alpha beta y1 plus y2. Okay, I just split this vector here into the sum of 2 different vectors. And you can see that this is 2 alpha x1, alpha x2 is actually LV1. Beta y1, beta y2 times 2 is actually LV2. So this is what we want to show. We already show that if we start with this expressions, we ended up with this expressions, which is the definitions of a linear transformations. Okay. by the definitions 2 times, again, by the definition 2 times alpha x1 and alpha x2 is alpha times L of V1. Okay, if you want to go another step, I can show you this. So this will be alpha 2x1, 2x2 plus beta 2y1, 2y2. Okay, and at this point, you see clearly that this is actually L alpha V1, and this is actually beta LV2. Okay, well, we just show that this map is a linear operator from L2, R2 to R2. All right, now let's take a look at, well, the next thing is want to provide a geometric interpretation for this map. What does it do? It's do if you have a vector in R2. So let's say I have, this is R2, right? And I have a vector here, 1, 1. Then when I apply the map L onto this vector, I will get 2, 2. So if this is V1, then LV1 will be the blue vector. All right, what does this map do? This map will magnify a vector by the size of 2. So it's increased the size of a vector by 2. Okay. Now go to the second example here. Consider the map L of x equals to x2 times e2. E2 is the one of the unit vector in R2. Okay. So if, for example, if you have an x vector represented by x1, x2, then Lx will be equals to x2 times e2, and e2 is 0, 1. So you will have 0 and x2. So this is the result of this map. Okay. Well, now again, you want to show that this map is a linear operator. Keep in mind that you always want to let v1, x1, x2, v2, y1, y2 in R, right? The two arbitrary vectors in R and alpha and beta as in R square. Okay. Well, now again, we just want to start with the left side, which is L, alpha v1 plus beta v2. And we know that alpha v1 plus beta v2, what is alpha v1 plus beta v2 equals to alpha x1 plus beta y1, alpha x2 plus beta y2. Okay, so from this information, L alpha v1 plus beta v2, using this map definitions, is going to be x2 multiplied to e2, which is 0, 1. So it's just going to be 0 and x2. 0 and x2 is alpha x2 plus beta y2. Okay, so this is the result of this transformations. And now again, the goal is we always want to show that this here equals to alpha LV1 plus beta LV2. Okay, are they equals? From here, because I'm coming from one vector, right? And I want to show this vectors here equals to 2 different vectors. That means I have to split this vector into 2 different parts. So I can split this as alpha 0 x2 plus beta 0, y2. And alpha plus times 0x2 actually is the same as alpha LV1, and beta times 0y2 is the same as beta LV2. Okay, so that's why this left-hand side here equals to this right-hand side. So we finish this problem. So we show that this map is a linear operator. Now the geometric interpretations of this map is, if you have a, again, we're still in R2, this is X, this is Y. If you have a vector, let's say 1 and 2, right here, this is the vector 1 and 2, let's say vector V1. Then if I apply this map L onto this vector, the result vector will be 0 and 2. So this is LV1. Okay, as you can see that the map here, this map will project a vector onto the y axis. Okay, so it just take the x2 is reserve the value of the second coordinate, and it makes the first coordinate equal to 0. That means you're projecting a vector onto the y-axis using this map. All right, so those are two examples of linear operator when you mapping a set of vectors from one vector space to some set of vectors in the same vector space. What if you have two different vector spaces that you're working with? Then how can you show whether a map is a linear operator or a linear transformation or not? Okay, so you have the map from R2, R3 to R2. So this map L here is a map from R3. Take some vectors from R3 to R2 to a set of vectors in R2, okay? And we want to show that this map here is not a linear transformations. Let's see. So again, I always have to call out two vectors and two scalars, V1, X1, X2, X3, V2, Y1, Y2, Y3, alpha, beta are in R. So these vectors here, you need to make sure that people know where your vectors are in. So this is in R3, and alpha, beta are just scalar. Okay. Then I'm going to start from the left side, which is L alpha V1 plus beta V2. And we know that alpha V1 plus beta V2 equals to alpha X1 plus beta Y1, alpha X2 plus beta Y2. Let me write down another time. So alpha V1 plus beta V2 equals to alpha X1 plus beta Y1, alpha X2 plus beta Y2, alpha X3 plus beta Y3. Okay. And then from here, you can apply the map onto this vector to get 1 as the first coordinate. 1 plus x1 is the first coordinate, and x1 is this guy right here. It's going to be 1 plus, well, I'm going to change a different color so it's easier to see. So this color. 1 plus x1 is alpha x1 plus beta y1. That's the first coordinate. And x2, it's just, this is the x2, is alpha x2 plus beta y2. So this is the result vector after applying this linear, applying this map. Again, the goal is, if this is a linear transformations, at the end of the day, you need to make sure that this left-hand side equals to the right-hand side, which is alpha LV1 plus beta LV2. Are they going to be the same? So I will try to, so in order to show this, maybe I will try to split this vector into two different vectors, right? You can try to split it alpha and alpha together and beta together. So we'll have, the best I can do is first I want to take 1 plus alpha x1 and then alpha x2, right? And the leftover is beta y1, beta y2, okay? So 1 plus alpha x1, alpha x2 actually equals to alpha LV1, but beta y1 and beta y2 is not the same as beta LV2. That's why this is not a linear transformations. So this linear here, this map here is not a linear transformations because I cannot go from the left side to the right hand side. All right. Now let's go to the next example here, example number 4. I have another map that is mapping some vectors from R2 to R3. So the linear, the map is L R2 to R3. Okay. Well then, I need to call out two vectors, but whenever you call out two vectors, you need to call out the two vectors from this vector space. So x1, x2, v2 equals to y1, y2, alpha and beta are in. So these vectors here are in R square. Okay, here. And alpha and beta are just constant, which is in R. Now I want to go from one side to another side, alpha v1 plus beta v2 equals, I'll do it real quick. So x2, x1, x1 plus x2. So x2 will be alpha x2 plus beta y2, x1 alpha x1 plus beta y1, x1 plus x2, which is alpha x2, alpha x1 plus beta y1 plus alpha x2 plus beta y2. Okay, and then when I split this into two different vectors, I will have alpha x2, x1, x1 plus x2 plus beta y2, y1, y1 plus y2. Okay, and this is actually equals to alpha LV1 plus beta LV2, which shows that this map is a linear transformations, right? This is the linear transformations that I just show that using the definition. And then you want to find a matrix A such that Lx equals to A times X. Well, that's the goal here. So in order to, well, we can try to guess the matrix A. I'm kind of running out of, so A, matrix A, okay. So it's a matrix, when you multiply the matrix to the vector X, you got the same result when you apply this map onto the same vector, right? Let's see, well, can you guess what is the size of the matrix? So the maps go from 2 to R2 to R3. Then I can try to guess, right, that L would take, so you multiply a vector, let's see, so if this is A and if I multiply to X, A multiplied to x, right? And this is a, and this is x. So the x will be from vector 2, the vector x is from R2, so x1 and x2. And then the result will be a vector in R3, okay? Then this is the result, ax, you should have 1, 2, 3 is the vectors in R3. So this is 2, if you look at this one, it's vector 2 by 1. And you have 3 by 1 as the result. Then what should be the size of A? The size of A, first I know that it has to be 2 here, right, in the middle. And then the result is 3. So the size of A has to be 3 by 2 multiplied to 2 by 1. You get a vector 3 by 1 or a matrix 3 by 1. What does it mean? That means you will have 3 rows and 2 columns. 3 rows and just 2 columns. That's what matrix A looks like. Okay, so then you see that, and you can see and look at the result vector. I will have x2 here, and this is x1. So in order to take x2, remember we have 3 rows and 3 columns here, right? So what is the first row? What does the first row look like? When you take this row and you multiply by this vector, you get x2 as the result. So it should be 0, 1. Right? Because when you do the dot products, it's going to be 0 times x1 is 0, 1 times x2 is x2. So that works. But the result of the second entry is x1. Then what should be the row of A, the second row of A? So then you take the second row, you dot products to the vector x, you get x1. You can guess that it's going to be 1, 0. Okay, because it's like 1 multiplied by x1, you get x1, 0 multiplied by x2, you get 0. So the result is x1. All right, so then the third entry of the result is x1 plus x2. Then what should be the row vector, the third row vector of A, that when you dot products to x1, x2, you get x1 plus x2. My guess is 1 and 1, because 1 times x1 is x1 plus 1 times x2 is x2. So this is the matrix A that I just formed, right? Such that when you take this matrix, you multiply by a vector in R2, you get the same vectors as when you apply this map onto the same vector. So I found a matrix. And you can see that this map here takes vectors from R2 to R3. Then the size of matrix is 3 by 2. So it's just a little reverse when you think about the size of a matrix. And later you learn that this matrix here is a matrix representation of the linear map. Of L. It's a matrix representation of L. All right. Well, here's some properties of linear transformations from one vector space to another vector space. And this also applies to the case when V and W is V. Well, linear transformation mapping a vector space V into a vector space W, then when you map a zero vector on V, you get a zero vector in W. And if V1, V2, and Vn are elements of V, and alpha 1, alpha n are scalars, then when you apply a map, the map L, onto linear combinations of V1, V2 to Vn, you get the same results as alpha 1, L1 plus alpha 2, L2 plus alpha n, Ln. This is more or less like the extensions of the definitions of linear transformations when you have more than two vectors. Okay. And the last properties is if you map on a negative opposite vectors of V, then you get negative map of LV for all V in V. Okay. So these are the three properties of linear transformations from a vector space to another vector space. Okay, here we go. This is an introduction of linear transformations. You learn about the definitions of a linear transformations from a vector space to another vector space. If you taking some vectors from vector space and you map it to the same vector space, then it is called a linear operator. And when you try to show a map is a linear transformation, you need to show that this equation is true. In order to show that this equation is true, you need to call out two random vectors in V and two scalars, alpha and beta. And then you need to start from one side and you want to end up to another side using the map descriptions. And I just show a few examples on how to show a map is linear transformations or not, right? By just using definitions. And always keep in mind that when you call out two random vectors, you need to make sure that these vectors here are in the appropriate or in the corresponding vector space, which is from this vector space. And then the result will be a vector in a different vector space. Okay, for example, I was calling vectors in R3, and then after I apply this map onto the combinations of these two vectors, I will get a vector. The result vectors that I got from this map is a vector in R2. Okay. And then for each of the linear transformation, you can find matrix representations for linear transformations. And we just found this is a matrix representations for this linear transformations. That means if you multiply this matrix onto a vector, is the same as apply a map onto this vector. And here are some three properties of linear transformations.